Hi everyone, how are you? Fine. Okay, ready for a battle? Okay, let's do some SQL today. And especially, let's do some performance tuning. And let's talk about performance and SQL performance tuning, especially from the coding perspective. So performance tuning is a very common stuff that we do in SQL Server. I always wonder why is that. Anyway, we should have a reason for that, I believe. So I choose to talk about a specific customer case study today. And I call it a performance battle. And that's because it was a very interesting case for us. And there are some lessons learned. We always have some lessons learned, of course. But the interesting story was that it was a company that developed his own solution. They had a lot of databases. They had developed a solution for constructing industry. And the problem they had was that they started to think about SQL Server when they received complaints from the customer, which is not a surprise. It's something that we do usually like this. We start thinking about the way we code in SQL Server when we receive some complaints. And this is the first part of our battle. So this is where our battle starts. And the reason I like that customer was that they had every single worst practice for SQL Server in a list of issues we found. So it's a typical scenario which I use in my trainings, and the single customer gave me everything that I need for building my training and classes and sessions. So they had everything. They had issues with the database administrations. They had issues with the configurations, with the tuning of SQL Server, with the way they spread databases physically on drives. They had issues on some important configuration settings on instance and on the database level. So what was our approach, actually? So first of all, the battle started, as I mentioned, when they heard the customer complaining. And the complaints were very common, like a slow response time, like a timeout of queries, like users feel like system was hanging. So those are the issues, especially when we work with a production SQL servers, that happen very often. And what we found, actually, after spending about 2 weeks at a customer side, was we found substantial issues in the SQL Server layer, and we managed to group them in 3 major groups. So our first group was issues with a misconfiguration in database maintenance. So I'm not going to cover them right now because it's a whole new, different topic. So they had a non-effective and non-scalable and a very expensive code running in their data access layer on the database side. So about this one I'm going to talk today. And they had a very common also database design and schema issues. So as I mentioned, they had all. They had everything that I needed to do 2 things. First of all, to be sure that I'm going to win that battle. And the second one was to be sure that they will feel like winners after they complete everything from the audit report. So we had those issues after we did several things, several actions on the customer side. So first of all, we fixed the configurations, we fixed the maintenance plans, we fixed everything that a DBA should do, but they didn't have a DBA. So we played that role. We managed to balance, to achieve some kind of balance of the configurations of that SQL Server. So we managed to stabilize the environment. Stabilizing the environment meant, in that particular case, that we managed to drop the extra workload. So they had a huge amount of extra workload running on that SQL Server. For example, someone has been advising them to run a monitoring tool. And there were 3 advisors on that one. And they have been running 3 monitoring tools, capturing all the sessions and all the workload inside the database. And this was extremely high as a workload that they have been generating on that database. So we stopped everything. We managed to release the peaks, the peak workload on the SQL Server stuff. And the main thing was to get that server up and running at least, to get that server balanced from the resource-consuming perspective. So the next part actually was to isolate the expensive code. So our second phase of our performance tuning project was to try to isolate the expensive code that they run and to try to advise them how to fix that code. And this is something that I'm going to show you right now as a most typical, most common scenario of running expensive code in SQL Server. Of course, if you are creative enough, you will find a lot more of them, but at least this will be something from my experience that is very common on a customer side. So we managed to isolate the expensive code, and I'm going to show you the common things, the common code that run issues in SQL Server, at least the one that you don't expect either to be expensive. So at the end, they were pretty happy that they know how to plan, how to fix things, even if for some fixes they needed to do completely rewrite to their user-defined functions, for example. Yeah, that was not a good example of a good advice, but still, thanks God, we have SQL Server 2017, and it gives us at least one more option to test our expensive user-defined functions in SQL Server and to have an idea if they will work or not, or if we need to rewrite that code, or we can just migrate to SQL Server 17. So in every battle, you need to have a strategy. You need to have a plan. And our plan was to do those 5 points, those 5 actions. Our first actions, as I mentioned, was to check and to fix configurations. This is a very important for every production SQL Server. So this is completely or entirely a database administration task. I'm not going to dive into that one. But it's important, the max degree of parallelism, the max server memory of SQL Server, those settings are cost threshold of parallelism. Those settings are how you set a database options at a database level, or to disable the auto-shrink, to make sure that the auto-close is disabled also, to optimize for ad hoc your SQL Server, which is also a setting. So all those settings are like checklists that every DBA should know, and every DBA should take care about having them correctly defined in a production server. So after getting that, we capture a baseline. So a baseline is kind of a milestone that you reach at the performance tuning project in order to get something like, did I manage to do something with that SQL? Did I manage to optimize the resource usage, or just I'm staying at the same place? So the baseline is the performance counters that you do, that you capture. We use performance analysis for logs as a PAL tool. We use weighting statistics in order to get the idea where the pain point, where the bottleneck is of our SQL Server instance. So weighting statistics tells us which type of weight is the most common for that particular SQL Server. And it's important to get that weight statistics before you do something as a performance tuning effort and after you fix some configurations. So we do statistics, we check statistics of our virtual file stats, which means the I/O statistics per server, per database, per file. It's important because after you spread databases physically on different disks, you will be able to check if you have managed to balance the I/O workload on your databases. So this was our fast fixing approach. So after being able to do that, after finishing that one, or before going to expansive code, what we managed to do, what we managed to achieve was the following, just as an idea. So this was our before state here, and this is our after state. So what we managed to achieve was to reduce greatly the pressure that this subsystem had on the disk subsystem. The pressure to memory and the pressure to disk. For SQL Server, this is critical from the performance perspective. So we are very sensitive of every single disk I/O operation that we have in SQL Server. So in case the disk subsystem is overloaded, then we definitely will feel that as a performance problem in SQL Server. So we managed to offload the disk subsystem, and we managed to reduce the latency of the disk subsystem, especially for the disk where the databases reside and the critical databases reside. So we managed to reduce the response time for writes, which was a great achievement because this is a transactional system. So this is a transactional database instance that holds transactional databases. This was something that we did just by not touching any code, just by managing to fix the configuration, just by fixing the configuration part. So they even couldn't make it for getting more memory on the server because it was a complex, very complex procedure from their management perspective. So we didn't have any more disk, we didn't have any more memory, so all we had was just parameters that we play with inside SQL Server. So, but the problem was that even after balancing the disk subsystem, we actually noticed that our next phase is coding issues. And why is that? So I'm going to show you something very interesting from the CPU perspective. Here we go. So the before and after stage actually shows us that we don't have many improvements on the CPU perspective. So obviously, we still have a very expensive code that runs on our SQL Server instance. Besides that, the things that remained in our SQL Server was, well, this was something interesting also. It remains to tune the batch requests per second. So basically, when we captured the first baseline of batch requests per second, which are the statement, the batches that you run against SQL Server in every single second, we had this in the beginning. And when they saw that, they said something like, oh, this is our SQL Server heartbeat. Well, almost. The problem was that it was way higher than a regular workload. So as you can see, the picture after, we had removed that heartbeat because this was something that is actually a very expensive extra workload that I had on that SQL Server. But we managed to get that only after the first baseline. So what they had was, they had a SQL Server replication. They replicated a lot of comments from one database to two other subscribers. The problem with that was a single store procedure. So a single store procedure the store procedure was written several years ago when they had just 100 rows in a single table. So in that store procedure, the logic was something like this. So they update all the records with the value of 1 of a single column, and after updating all records to value of 1, they update just some of them to value of 0. So updating all the records as a logic was something that worked several years ago. But now in that table, they had 3 million of records. So having 3 million of records and updating everything, every single record to a different value, meant that the publisher was generating 3 million of comments, which were transferred to a distribution database. And after that, like a wave, they transferred that workload to every single subscriber. And this is the heartbeat that they had on that SQL Server. So we allocated, we identified that store procedure, and they performed, of course, they changed the logic of that store procedure, so we managed to reduce greatly that particular heartbeat. They still have it because they need to modify some records, but at least not 3 million of records every single hour. And when they had that 3 million of records updating every single hour, and if this matches a store procedure or a logic that they have running on a regular basis on their workload, so they had a lot of timeouts at the end. So this was the main reason of most of the timeouts they had. Still, we have something, we had some issues that remained still after performing the configuration. So our issues was running expensive code, consuming too much CPUs, still having peaks in I/O operations. So our next task was to identify the expensive code, to be able to understand which store procedures, because they rely entirely on store procedure code, style, and we needed to identify the expensive store procedure, which are those which consumes the most of the workload, the most of CPU resources, let's say. So after code analysis, we managed to identify some problem code, and of course not all of them, but some of them are very, very common, and we have that in almost every single customer that we do performance tuning on. So the first coding problem was about parameter sniffing. So do you know what how many of you knows what a parameter sniffing is in SQL Server? Okay, a few of you. So a parameter sniffing actually is a feature. It's not a bug, it's a feature in SQL Server. So it's the way SQL Server works with execution plan compilation. So the whole compilation process, the whole style of using a store procedure relies on the parameter sniffing in SQL Server. So let me give you an example of that. Why is that so expensive sometimes? Because we have a bad parameter sniffing, so we rely on sniffing parameters during the compilation of store procedures in SQL Server, but sometimes it's a very, very expensive from the resource consumption perspective. So here is an example, a very simple store procedure, just in order to get an idea what a parameter sniffing is and why it just doesn't work for us at some cases. So I'm going to create that store procedure, and the only thing that this store procedure does is just a single, very simple select clause. So I have a single parameter, and this is something that I'm going to show you, so how it works. And I'm going to show you the execution plan of that store procedure. So the first execution plan, the first time I execute that store procedure with the first parameter value, SQL Server will sniff that value. It will read that value, 11005, and it will build an execution plan for that particular store procedure. So the execution plan of that procedure will be saved in memory. And potentially every single session that will use or will start that store procedure from now on will use the same execution plan. So this is a parameter sniffing, or the way parameterization works in SQL Server. So that the whole goal of parameterizing code in SQL Server is to reduce the compilation time, to reduce the amount of CPU resources that a compilation consumes, the compilation process consumes. So how the execution plan looks like, actually. So I have this. I'm not going to dive into that one, just some important information that we can understand for that particular execution plan. So we basically have a so-called bookmark operation that we do in SQL Server. So I'm searching for a customer ID. And because I have an index on the customer ID, so I'm performing an index scan operation first in order to get to the particular value of a customer ID. So performing index seek on non-cluster index is followed by performing a lookup into a clustered index. So let me give you an idea, just roughly, how this works. So if I have this as a columns as a clustered index, so this is a B-tree structure, then I have my sales order IDs of my sales order table ordered and stored into my leaf level of the index, which is my bottom level of the index. So those are records that are saved into data pages. So every data page in SQL Server has a number, and they are consequently ordered into the file structure, into my database file. So I have those pages, which are index pages. They stay on top of my leaf level index structure, and I have a root page which stays which acts as a first page for starting a seek operation. So I have an index key stored here on my index level pages. So I know that my sales order ID, starting from 1 to 7, is stored into the page 12561. So if I search for a particular sales order ID, then I usually start from the very root page, from here, for example. Let's assume that I'm searching for sales order ID 7. Then I start from here. I go to that particular page, so I'm interested in that page. I go to the next level. So I go to that page. I know that my sales order number of 8 is stored on that page because it stays between 7 and 13. So my next page in my seek operation will be that one. And going to that page will allow me to read my sales order ID. So this is my clustered index seek operation. So what about having a non-clustered index operation? So a non-clustered index is an index that we built on top of the clustered index in order to get a different sort order. Like, for example, we have a customer ID, non-cluster index by customer ID. So in our non-cluster index by customer ID, we have a leaf level of the index, which are actually index records. Those pages contain index records. So what I do is to find a customer ID. Then I found a customer ID by searching that column. I go to a particular page here, like for example this one, and what I found is a pair of records, which is a customer ID, sales order ID. So my non-cluster index contains just a pointer to a clustered index key. And my bookmark operation means that I perform 2 logical reads here. So I'm reading that page, and I'm reading one of the pages which stays on the leaf level of my non-cluster index. So by getting the value of my sales order ID, I go back to my clustered index structure, and I'm doing that traversing index operation starting from root page, going to the next in line, and ending up to the page where my record resides. So I'm doing 5 logical I/O operation, which 2 of them are seek operation on my non-cluster index, 3 of them are seek operation to my clustered index. And because SQL Server knows that I'm searching for a particular customer ID like this, the particular customer ID is actually, it thinks that, it estimates that I'm searching for 2 customers, approximately, and it gives me actually 2 customers at the end of query execution. So for 2 customers, it's worthy to perform an index seek operation or a bookmark. And it takes 8 logical I/O operation because I have 2 customers which I'm searching for in my non-cluster index, and I have 2 customers for each of which I need to perform 3 logical I/O operation, or searching for 3 pages or reading 3 pages. So this is something that creates a very good execution plan for me, but it creates a perfect execution plan, a very cheap one, because it sniffs my parameter. So it stays, my parameter, compiled parameter is this one. So my execution plan is actually built for that value of the parameter. So if I run that same parameter, that same store procedure with a different parameter, then what I will have is, by design, I will reuse the same execution plan. But now I'm returning actually 10,000 of records. So the estimation of my execution is still 2.1 because the execution plan is reused. But the actual number of rows is 10,000. So instead of doing 8 logical I/O operations, I'm doing 30,000 I/O operations. Because for 10,000 of rows, I'm doing the same bookmark for every single row. I'm traversing index, non-cluster index, and the cluster index. So this could be a really expensive execution of that particular store procedure. So the point is that in SQL Server, the store procedures and the compilation logic, the compilation concept is designed with something very important in mind. So they have designed that by assuming that our records are spread evenly in our tables. So we have an even distribution of records, but it's not true. It's not something that is true in a production real environment. So you can have sales orders for particular customers which are way bigger numbers than for different customers. So we have this difference. We don't have an even distribution of data in our SQL Server. So basically, this is the problem that could be very important even if we have more complex scenarios, like more complex statements. So imagine this one. So I have a where clause which is between modified data. I have a between and clause, and I have an order by. So my order by clause means that I will need to sort those data in memory. And if I start this again, my first execution of my store procedure will dictate the execution plan for every next execution of that store procedure. And what I have here is that I have this sort operation. I haven't still an index seek. I have a sort operation, and the sort operation expects to sort one row. So by expecting to sort one row, it will allocate a memory in SQL Server instance, which it will be enough for sorting one row. This is 1 megabyte of memory. When I run that store procedure again, but when I put a different interval different value for that parameter, I will get more rows at the end, and I will still be able to sort those inside the 1 megabyte of memory. But what if I put something like this? So I make interval way bigger. Then in that particular case, you can see the result shows a warning in my plan. So this is a very simple query, by the way. It's not something that you will feel a difference in the duration of the query. Even we don't feel the difference in the CPU consumption. But the problem is that if you run that query in your production environment, and it's a very complex one, then this sort warning operator that you gain into your execution plan will mean you work inside the TempDB database instead of working in memory. So, well, when SQL Server is not able to sort those data inside that memory amount, like 1 meg here, then it will not increase that memory during runtime. It will just continue to work inside the TempDB. But the TempDB is not the same as from the performance perspective comparing to working in memory. So you will have that as the increasing of the CPU time. As a result of that, will be increasing in the CPU time and increasing in amount of I/O operations. So those queries are very expensive in SQL Server. So what is actually the solution of that case? Well, they have something new in SQL Server 2017. They have this called adaptive memory processing or adaptive batch processing. And they try to adjust the memory setting during the execution time. So if I run that twice in SQL Server 17, then the memory grant will be adjusted based on the number of rows that I run in my query. And as a result of that, I will not have that TempDB consumption. So our next reason of running a very expensive code or having an expensive executions in code was this very complex, let's say, where clause that we found into the code of the most expensive queries. So imagine that we have a requirement to build something like this as a functionality, which is called dynamic search. So is this where clause something that is familiar to you? I mean the style of writing that where clause. How many of you have seen that into the code? Okay, great. Now let's see what you do in your code at the end. So what is the problem with that clause, actually? So the problem with that, actually, developers sometimes are very proud of that where clause because they write less amount of code and they manage to build a complex logic inside a single where clause, which is actually true. But from the code perspective, I mean, yeah, okay, you write less code than usual, but still, it works very bad in SQL Server, by the way. So what the problem is, so imagine the following scenario. So I have indexes. I have built a separate index on last name and on first name. So what I do is to create that procedure. And when I first run that procedure, with the last name value of my parameter, then my first run, remember the rule, my first run will dictate all the runs that I have on that stored procedure from now on because it will build an execution plan. So the execution plan will be built based on the last name index. Why is that? Well, because it will sniff the last name as a value, it will see that I have a last name as a value, and it will perform an index seek operation on member last name. It will say, hey, I have an index on last name. So I will be able to satisfy that query, and it will be very fast. So okay, that's okay. But what if I run the next one? So now I have tautological reads. I have a very good plan. But next time, I run the first name with the parameter first name. So now I'm using the same plan. So imagine I'm using the index on last name in order to get the first name. So that's completely ineffective way of selecting data from a table. So at the end, I will have, here we go, because it will read all the data throughout that index. So it will try to perform scan operation, and that scan operation will be extremely expensive. So the problem is that the first parameter will dictate the execution plan for all the remaining parameters. But I have a dynamic statement, so I build a dynamic statement every single time. So it's not worthy, it's not proper to use the same execution plan just because I have a different statement. What is the workaround of that, or how to build such a code in SQL Server? So in that particular scenario, I had a where clause which contained about 30 parameters. So you can imagine the where clause was very big one, but still they had at some combination of parameters, they had that query running for hours. So with a high CPU usage, with a high memory usage, so this one increases the CPU a lot. So the problem is that for the first case, when I had this customer ID example, the workaround of that is to just perform something like this. So I'm getting back to that one. First, I will tell you the workaround for the next one. So here, the option that we have is option recompile, for example. So the option recompile hint, you can put that hint into your select statement in order to recompile the plan for that particular select statement on every single execution. So you don't put that on a store procedure level because it will cost you too much. I mean, compiling a store procedure could be very expensive from the resource perspective. Compiling on every single execution is also a very expensive workaround. So we just do an option recompile hint, or we can put an option optimize for unknown or optimize for a particular value in order to fix the plan of that particular select statement. So we don't rewrite completely the store procedure, because the reason of that bad parameter sniffing is actually the data itself. They are not spread evenly in our table. The problem with, so let me give you the solution of that one. So I'm altering that store procedure. I'm doing that one. So this is the workaround in case you have a data problem with data. And when I have that, when I run that one, I will still have, oh yeah, of course, I'm not in the correct database. So getting into AdventureWorks will help. And I will fix that by recompiling. I will run that one. So I will have the perfect plan for 11005. And now I will run that. And here we go. I have a cluster index scan for that particular select statement. So this is a workaround that we need to perform in order to fix the problem with our data in our database. what about this one? So this one could not be fixed with the option recompile, just because you have a different parameter list on every single execution of your select statement. So we generally build a dynamic SQL in that case. And that's why we usually write that code by using a dynamic SQL. And this is probably the best way to implement or to use dynamic SQL in SQL Server. So there are a lot of pros and cons of, or a lot of arguments against or pro dynamic SQL in SQL Server. To use it or not, how to protect your code. Of course, you need to protect against the SQL injection, but still dynamic SQL behaves perfectly in that particular situation. So let me show you. So basically, you built that query dynamically. Building that query dynamically means that you start by something that should work even if you don't put any parameter values in your stored procedure. Then you check every single parameter value and you build a string by just concatenating the next parameter value. At the end, you will have your own string, your own select statement built for that particular execution. So when you run that statement, I need to be on the credit database for this one. So when you run that statement, then every single execution will build a separate select. And because the dynamic select, dynamic SQL is an ad hoc statement, it will be recompiled on every single execution. So you will end up with a perfect plan for that particular select statement. Still, you don't recompile your stored procedure. Still, you use the stored procedure as a coding practice because it has a lot of benefits. But you overcome this parameterization problem in SQL Server. So let me show you. So now I'm building that statement. Oops. So this is my statement, which I'm executing right now. And this is the execution plan of that particular statement. So I'm doing that member name for last name. I'm executing that for the first name. Here we go. So now I have a different select statement. And because of that, I have a different execution plan. So here we go. I have a first name. If I do two parameters, then I will end up with this statement. It will be compiled, and it will use the member name because it contains both. It's a composite index, which contains first name and last name column. So basically, when we have these dynamic search conditions or dynamic search requirements in your stored procedure, which is a very common requirement, you basically don't do that where clause. You don't write that where clause. It's the best way to do that is to use either dynamic string execution like this, or you can even help yourself to work less by avoiding the SQL injection part and by using the SP execute SQL, which will check your parameters instead of you. So this is also an option. So those are the most common ways, the most common scenarios that we had in SQL Server for that particular customer. And if I go to the most expensive queries, so this is the report, part of the report that we performed for our customer. So you can see something very specific, very common. So those are the most expensive procedures, the most expensive modules ordered by the amount of resources that they use. And as you can see, the top three are functions. And those are user-defined functions. So how many of you have experienced some weird execution behavior by using user-defined functions in SQL Server? Yes, okay, a few of you. What's the problem with those? Actually, in order to explain you the problem that we have with the user-defined function, I will switch to SQL Server to a virtual machine that I have built for that, and which contains SQL Server 2017 installed. So it's not just because I want to show you how the SQL Server 17 behaves in that scenario, but in order to compare the behavior of user-defined function and what they did in SQL Server 2016 to start fixing that issue. So we have that issue in SQL Server since day one. Since they built SQL Server user-defined function in SQL Server 2005, I think, or earlier. So the user-defined functions don't scale well. They don't scale. They behave badly when you increase the amount of rows that you process by user-defined functions, and this is the reason why. So I will use a very simple user-defined function, and the user-defined function is something like this. So I have top and factors. It returns the function returns table like this with that structure, and the body of my function needs to have statements which will insert some data, which will fill that table. This function is called multi-statement table valid function in SQL Server. So basically, it returns table, and you never know how many rows that table will contain. So I'm going to create that function in my worldwide importance data warehouse, and I'm going to switch my database into 110 compatibility level, which means SQL Server 2012 behavior. So my goal is to simulate the SQL Server 2012 behavior. So I'm going to run that. There we go. And I'm going to use that function into an ad hoc query like this. So I don't want to return rows. I want to just run something that uses my top function. That's why I'm just using the count star. And I'm joining my table with my user-defined functions. And I want my user-defined function to process 20,000 of rows. So what will I do here? I will include the actual execution plan. So it's kind of slow, as you can see. And the execution plan, I'm not going to read all that, but I'm going to show you something important here. So the function has this estimated number of rows. Here we go. But the actual number of rows that goes through that function is 20,000. The estimation that SQL Server uses for that function to run or to compile the execution plan is 1 row. And probably you will not believe that, but it's hard-coded in SQL Server. Yeah, it is. We have every single time that you use a user-defined function in SQL Server as part of your code, SQL Server will build your execution plan with 1 row as an estimation. So it will always think that you will process 1 row in your user-defined function. That makes your execution plan very cheap, actually, because you process 1 row. So getting 1 row means that the whole plan will be very cheap, but it's not, actually. And it will never run in a parallel execution. And it will never build a proper plan for user-defined function. So, and because of that, we'll try to check if there are some improvements in the recent version of SQL Server, like SQL Server 2016. So let me switch that database into 2016 mode. And let me run that again. Here we go. So now they made some improvement. Can you believe that? Come on. Yeah, okay. So yeah, you can think of it, it's 100 times faster, but it's not. Or it's 100 times better. No. So at the end, you will have the same. So basically, you will have the same execution plan, but still the discrepancy is huge. So even in SQL Server 2016, it's not something that you will have as a good experience when you use a user-defined functions in SQL Server. So yeah, they got a huge amount of messages as a SQL Server program group, I mean. So they started working on that, and they built something in SQL Server 17, which is called interleaved execution. So let me switch that database to SQL Server 140. And if I run that, then what I will do, yeah, it's improved. Actually, you can see a lot of warnings here, but it's kind of normal. I mean, okay, I'm going to run that again. And yeah, I'm not going to dive into those warnings, but the point is that at least we have that. And the reason is that they changed the way they run user-defined functions in SQL Server. So during the compilation time of your ad hoc statement, they run user-defined function. They just run that function during the compilation time. They get the actual number of rows that goes through that function. They use that number for compiling your ad hoc statement. So that's why it's called interleaved execution, because they first execute a user-defined function, they use the result into your ad hoc statement, and they build your ad hoc plan. So there is a light into the tunnel. We can still use user-defined function, but in SQL Server 17. And the improvement is just for SQL Server table-valued, user-defined, table-valued, multi-statement use functions. So if you have that function, then you can use that as a benefit of a new version. So. But we did that in March this year. So we did that performance tuning of our customer in March this year. And yeah, you can imagine the reaction when I managed to isolate those user-defined functions as the most expensive query, as the most expensive code that they had. And when they asked me, well, okay, how to overcome that? And I said, well, you need to rewrite those. What? So we have dozens of them in our code. I said, yeah, okay, I know, but yeah, you still need to change to choose a different solution for that. So this could be painful. This code rewriting stuff, I mean. So the remaining things that they had into the code. I wish I had one more day to talk to you about performance tuning at least, but yeah, but still, yeah, I can talk weeks about issues in SQL Server, but we need to, yeah, I need to some kind to compress that into 5 minutes. So they have a very ineffective code iteration. They used cursors for implementing some logics, which is absolutely not relational, and the SQL Server is not optimized for that. So you need to, in order to avoid issues with a bad code, you need to keep into set-based operations. So iterating through records row by row is not a good thing at all. So we had, we found some common issues into schema level also. Well, those are really hard to fix sometimes because fixing a schema in the database is something that hurts. So it requires a lot of changes. It requires a lot of changes in your code sometimes, so it's not easy to do that. So the first things that we had was we found an improper primary key. So in SQL Server, when you define a primary key, you define a clustered index column. So you build a column structure, you build a B-tree structure, which is your clustered index. But imagine that you build your clustered index on not on an ID or not on an ever increasing column. So in that case, you will have an insert that will need to go to a particular page, not to the end of the structure. In that case, going to a particular page when a page is full means that SQL Server needs to perform a page split operation, which will be very expensive comparing to a regular insert at the end of the structure, comparing to adding records at the end of the structure. Imagine that you have built primary key by name or by social security number, let's say. So in that particular case, you will need to insert into a single page. And if the page is full, then SQL Server will do a page split operation, which means allocating a new page somewhere in the file and moving half of rows from your main page to the new one. And this operation is fully logged, so it performs a lot of IOs to the transaction log file. So having that in mind means that we need to take care about which columns we choose for primary keys, which columns we choose for clustered index. So choosing improper columns for cluster index means that we will end up with a very expensive, very slow inserts. We will end up with a fragmentation of our indexes. And at the end, we will read more to satisfy our queries than we should read from the disk. And last but not least, is they had a lot of data type mishmash, which means they needed to perform an implicit conversion in SQL Server. So it's important how you compare data in SQL Server. And what do I mean is when you need to make a where clause, then on the one side stays a column type, on the other side should stay the same data type. If SQL Server needs to perform an implicit conversion of your data column, then you will end up with an effective plan. So it does matter if you compare strings, for example, and if you define your variable as var character and your data column is nvar character, then SQL Server will convert your data column, your column from the table, to the type of the variable before satisfying the where clause. So but the problem is that it will not do that during the compilation. It will do that during the execution time, which actually means that during the compilation, it will not know the cardinality of your query. It will not know how many rows the query will return, and it will not produce the most effective plan for your query. So keeping with the same data types when you use the where clause, when you build the where clause, and when you build the join clause is something that is very, very important. Because if you have to join on a different column types, to tables on a different column types, then probably SQL Server will make Cartesian product of your tables. And you will end up with a huge amount of IO operations. So the data types or data types equality is something that is critical in SQL Server. So of course, I'm not talking about missing index, extra indexes, because this is a whole new topic, but still, this is not that important. This is even not the most important thing for your performance. There are different things in the coding and in your schema that are way important for building a foundation of a good performance. Because according to indexes, your database administrator could capture the workload, could analyze the missing indexes, and could build the index every single month, or could remove an extra indexes. So this is a dynamic operation. This is not something that we do from the very beginning of our deployment, and those indexes will not stay to the very end. So we actually adjust those indexes from time to time. So you can still win a performance battle in SQL Server. The things that you need to take into account are, you need to have an approach. You need to start from somewhere. The problem is to find the problem with the most weight of your performance issues. So in our case, this was user-defined functions and parameter sniffing and data type mishmash, actually. So they knew how to fix that. We found that if they focus on that, they will have about they will have a lot of improvements. The story was interesting because they had yet another problem, which was they had a different collation between those databases, and they had some views which relied on those on different tables in those different databases. But the problem that we saw that, and we thought that this is the main problem, and the problem is actually that the workaround is to export the data from the database and to load that into a new database. So you can imagine that it takes a huge amount of efforts to fix that. So when you start investigating a performance tuning issue, then you need to understand which problem is the most important one and which problem will gain the benefit when it will be fixed, after it will be fixed. So in that particular example, collation was not a problem, was not the main problem. So thanks God, we realized that in the very beginning of our code analysis, and we didn't recommend changing collation of the data. So the problem which has the most weight is the most important to identify in the code research. So we search for the big wins first, and those are configuration fixes that we perform usually as part of the performance tuning project. So you need to measure your result. You need to see what you have done in order to understand what is the next step. So thank you for listening today. I wish you a very good conference and a very good day tomorrow. See you next time. Please fill the form. Thank you.